Section 13.7, Satellites, Orbits, and Energy. We have a ton of satellites just around the Earth alone, and we're sending up more each day, it feels like. Lots at once. If you check out what Elon Musk is doing. Pretty wild. So we want to be able to understand a little bit more about their orbits and be able to describe their energy. So if we want to be able to describe their orbits, we can describe the kinetic energy if we just think through the gravitational force and how it relates to our centripetal force or centripetal acceleration with F equals ma. So it all goes back to F equals ma, right? Our gravitational force is big G, big M, little m, all over r squared. And since the satellite is traveling in a circular orbit as it goes around and around the Earth, we know that it does have acceleration. What kind? Our centripetal acceleration, which we can write as v squared over r. And we notice this mv squared, it looks a lot like our kinetic energy. So if we just multiply both sides by r, we can cancel out one of the r's in the left side, and then also multiply both sides by 1/2. So there's a 2 in the denominator. Now we have 1/2 mv squared is equal to g big M little m over 2r. It's a little hard to read, but it's already written for you right here. And this describes our kinetic energy. Notice this looks a whole lot like our potential energy, right? Our potential energy, we said, was negative g big M little m over r. So the only difference is that we are off by a negative sign or different by a negative sign, and then there's that 2. So the kinetic energy is negative 1/2 the potential energy. So if we want to describe the total mechanical energy, we can just add those two together. So we can add the kinetic plus the potential, and since the kinetic is half of the potential, the total energy is going to be half the potential, but negative. The negative of the potential wins out. So our total energy in a circular orbit is given by negative g big M little m divided by 2 divided by r. One thing we can notice here is our total energy is actually the same calculation as the kinetic energy. It's just negative. For an ellipse, instead of a circular orbit, instead of r, we would just substitute in a, the semi-major axis. And so the energy of the orbit depends only on the semi-major axis and not on the eccentricity, which is pretty wild. Here's an example of different eccentricities, right? E equals 0 is perfect circle. E equals 0.5, E equals 0.8, 0.9, it becomes more and more stretched outward. But all of these orbits have the same energy because they have the same semi-major axis, which is neat to see. Now that we have a way to describe the total energy, as well as the kinetic energy as a function of r, here's a plot of the satellite's energies versus orbit radius, right? So kinetic energy is this 1 over r on the positive side, and the total energy is the exact opposite of that. It's negative, the kinetic energy. And it's always at a larger value than just the potential energy alone, which is the most negative. And that is where we have it. All right, our very last section, 13.8, looks at Einstein and gravitation. So this is a little bit of an expansion into some more recent areas of physics. So the general theory of relativity describes gravitation in another way. Its fundamental principle is the principle of equivalence, and says that gravitation and acceleration are the same. How can we demonstrate this? Well, if we imagine that we have an experimenter, a scientist, who's in an elevator or a box with no windows. Well, the experimenter can't tell if that box is just resting on the surface of the Earth, and they drop the ball, they could measure how long it's in the air and see that, hey, that ball follows with the acceleration of 9.8 meters per second squared. But they could just as easily be in a spacecraft that's traveling at 9.8 meters per second squared upward, and then dropping the ball, it would fall at exactly the same rate. So those two situations are equivalent. It's equivalent if the experimenter is on a massive object like the Earth, or is just traveling with a huge amount of acceleration. So based on this idea, Einstein proposed an idea that space, or more thoroughly space-time, because space and time are interlinked, it turns out, that space is curved. What does this mean? Well, some analogies that can help us to visualize it. We could imagine two ships start out at the equator, separated by some distance, maybe 20 kilometers. And then as they travel to the South Pole, like, okay, see you at the South Pole, I'm gonna meet there, they notice they're getting closer and closer to each other, even though they're traveling straight to the South Pole. It's like, hey, is there something pulling us closer together? Why are we getting nearer and nearer? Or similarly, if we had two apples that were falling towards the Earth's surface, the closer they got to Earth's surface, the closer they would get to each other as well. And it seems like there's some sort of force that's pulling them together. We can see why not, though. Like, since we're not on those ships, we're outside the ships, we can see, oh, they're traveling on this curved surface. And so, yeah, based on that curved surface, they are going to get closer and closer as they're getting there, right? We're able to step outside the curved Earth to have some perspective on it. But we can't step outside curved space in the same way. We just have to imagine that maybe that is how things are. So we could imagine that space is normally flat, that there aren't forces pulling us one way or another. But if there's a really massive object like the Earth, then it can pull the sheet of space downward, right? Like putting a ball on a blanket and watching the whole thing bend downward. And that could then cause you to have these converging paths when you're coming from the flat space that's far from Earth into the curved space near Earth, right? Where the closer you are to Earth, the more force there is pulling you down into the Earth. And you may have seen this demonstrated with a gravity well, like with coins that are able to circle around in orbit at a lot of museums or kids' museums. Same basic idea here. So even though we can't step outside the curvature of space, we can observe the curvature of space. So the way we can observe it is that it turns out that light bends as it passes by massive objects. This is an effect called gravitational lensing. And in extreme cases, we can observe the light coming from multiple places or bent into an Einstein ring. So here's an example of this where there's light that should be coming to us from a quasar, something really bright. And then in between us and the quasar is this galaxy or a large black hole, something with a ton of mass, right? Well, the light itself is actually going to bend towards the Earth detector. And so it appears to be coming from not the very center of it where we say, oh yeah, it's right there. It appears to be coming from two places on either side of it. And that's what shows up in this image, right? Where instead of having the quasar right at the middle, we're seeing two spots and even a ring around. So the light has bent around this massive object. And that's really cool that we can see that space-time is curved by the effect of having massive objects there. Interestingly, though, the source of gravitation is still unclear. Is it purely an effect of this curved space-time? Is it a force between masses like Newton proposed? Or is it due to some fundamental particle, the graviton, which could carry the gravitational force and be the source of it? These questions, it turns out, are not yet settled. They're still being studied. Scientists are still trying to recreate the graviton, which takes a ton of energy. That's why we have particle colliders that have amazing amounts of energy. So science continues to venture further, and it's not that Newton's law of gravitation is wrong, it just might not be complete enough to describe everything going on. It only works in certain circumstances, and it is reasonable in that regard. That's known as the correspondence principle. So the newer theories will have to agree with Newton's law of gravitation, but they might offer us a more thorough understanding of where this gravitation comes from. Maybe you'll figure it out. Let me know if you do. So we will wrap up chapter 13 there. That is gravitation.